Hi, everybody. My name is David Beard. I'm the developer evangelist for Qualcomm Vuforia. We're Qualcomm's mobile vision platform. And so what I'm going to do today is to really introduce a feature that we're providing for digital eyewear. And this is for the range of optical see-through eyewear, which are eyewear with transparent displays, and also video see-through eyewear, which is what you're accustomed to with like the Gear VR. These are displays that use typically a mobile phone, and you're using the device camera to see the world around you, and you're actually looking at the device display. So Cardboard and Gear VR use a video see-through type of headset. And so what today's session is really going to cover is I'll give you a brief introduction to the platform, and then I'm going to talk about the features, some of the use cases that we've been enabling with this, how people are applying digital eyewear, how they're using us for both mixed reality with AR and VR apps, and also for immersive experiences and for experiences that are actually blending real-world elements into virtual reality use cases. And then we'll get into some examples. I'll show you a reel of some of the applications that have already been developed and some forward-looking applications that have been developed for example, driving applications. And then I'm going to get into a brief sort of overview of the workflow. We don't have a hell of a lot of time, so I'll just get you into the environment in Unity and show you some of the components and really what the basis of the workflow is. And then we can take some questions. So as I mentioned, we're Qualcomm's mobile vision platform. Really, our role, we've taken advanced computer vision algorithms, and we've built them from the ground up for mobile devices. And as you would expect, computer vision on mobile, it's a computationally intensive process. And so a lot of our focus has been in getting the best performance possible, really for resource utilization, thermal issues, the whole range of considerations that you get into in running computer vision on a mobile device, and also to provide the sort of rendering budget available that you can build high-quality applications with the sort of user experience that people expect of, mobile games and other advanced applications. So a lot of our focus, again, is taking computer vision, really refining it and improving it for mobile devices, and then making it accessible to developers who don't have any background in CV. CV is a pretty sophisticated topic, and a lot of our work has been in making it easy for people, making it simple to design and deploy and implement computer vision applications. And if you're familiar with Vuforia, you'll hear about us for augmented reality. And what that means is really the ability to recognize things in the real world, to understand where they are within the field of view of the camera, and to actually track them as they move, and then to render content onto them. So AR is famous for the ability to recognize images or to actually augment and render things into the real world so that it's realistic. It looks like you actually see that thing in the field of view of the camera. So here's some examples of what we've been doing. I think our audio is knocked out. But there you go. So what you've seen there, we've seen a huge uptake in the range of a lot of casual applications, branded applications, also adaptation for toys, retail experiences, and also enterprise and industrial use cases. The eyewear examples that you had seen with the woman working with the pump, or other things where people are visualizing architecture or visualizing products in place, basically. So again, the proposition is that we provide a very simple API that describes what the camera is seeing in the world around it. And the range of images and objects that we can track, really, what we're looking at is to recognize something and to actually be able to follow it is really the pattern of contrast variation that's on the surface of the object. So that's why if you see some of the applications that we're showing is typically the object or the image or the environmental features that are being tracked have enough detail that it can be actually picked up by the SDK. So as a design consideration, it's always important to understand that you need to work with something that has some contrast variation. There needs to be some detail on the surface of the object. But the range of things, again, we can track planar images, which is really like a rectilinear image, a flat image. You can also arrange images into geometric configurations like boxes or fans, so we can track objects that way. And we've introduced, as of really last year, the ability to track three-dimensional objects, meaning these are things like, let's say, toys or other objects that can be captured fully within the field of view. And we actually have the ability to generate a 3D model of that. We have an application that we provide that you can scan the object. It creates a representation of it that you can embed in your application. And it actually supports the ability to recognize and track physical objects in the real world and then to render content onto them. So we had pointed out some of that in the show reel, but one thing that we show is, for example, the vehicle demo. And it's a car that's like black and white. It looks like a toy car. And you'll notice that we're able to accurately register digital content onto the surface of that object, which is an interesting feature. We can recognize text, which is really like, the ability to recognize words, to recognize characters, to actually read paragraphs and to understand where they are within relative to the position of the camera. And we've introduced what we call smart terrain. And smart terrain is a reconstruction technique. You'll see people showing this now. It's like Tango does some of this. We introduced it over a year ago. But what it is the ability to actually reconstruct the geometry of a physical setting. And it's really optimized for, let's say, tabletop experiences. It's intended that you can actually reconstruct as a mesh, as a three-dimensional mesh, the surface geometry of, let's say, a table, and then to actually understand when there are objects on top of that, to segment them from the primary surface of the table, and to reconstruct them with a bounding box. So we can understand where there's a ground plane and when there are things sitting on it, and then you can apply physics and other techniques like rendering onto them and actually reconstruct an environment and make it a sort of virtual scene using real-world geometry. So to do all of this, we provide several flavors of SDK. We support Android and iOS for mobile devices, really for ARM devices. And then we have a single SDK that supports both mobile and also digital eyewear. So you can build an application for a smartphone or a tablet and actually then port that onto a digital eyewear device, again, like a video see-through or an optical see-through. I'll get into that in the next couple slides. But it's just, I think, the thing to understand is that, again, Android and iOS, we support Unity. Obviously, that's really most of our developers are using Unity. It's very easy. The workflow is primarily authoring-based. So it's like drag and drop. It's like a design workflow. And then we also provide SDKs for native development in Java and C++ that you can work in Xcode or you can work in Android natively. You can also develop plugins from those and bring them into Unity or actually embed Unity into a native wrapper if you want to. And we've been around for over 5 years now. We have over 175,000 registered developers, over 20,000 apps in market, I think 200 million app installs. So it's been very popular. And a lot of it is a testament to the fact that we're very easy to work with. So, what I'd encourage after I go through this, is take a look at our developer site. It's developer.vuforia.com. We provide all the SDKs there. They're free to work with. We provide samples that demonstrate all the features of the platform. And they're nice because they're really focused on that feature specifically, and you can use that as sort of a template to build your own app. So anything I'm discussing here, you can find a sample representing that at the developer site. So again, the offering, as far as the range of what we're providing with the platform, it's end-to-end. We have SDKs all the way through developer tools, and then online services that support the management of targets, the deployment of applications, and the ability to support very, very large-scale apps. So just quickly, to address these, again, the Vuforia engine, which is the SDK, we're supporting phones and tablets. We're supporting digital eyewear. There's 5 versions. You create and manage targets in the Target Manager online. That's at developer.vuforia.com. And that's really a web-based tool. You upload targets, you configure them, and then you can generate a data set or a database that you embed in your app. Now, there's really 2 ways to deploy targets. You can either embed them. You actually bring in the data set, you put it into the app, and you build that. Or you can use our cloud service. And the cloud service you can use the client SDK to query the service, and what it's going to do is bring in the same kind of target that you would embed into the app, but it delivers it online. So you can work with that from our SDK, and you can also develop content management systems using a REST API that interface with our cloud service to create large data stores of targets and to manage them, to version things, and do all of that. With our tools, again, there's the target manager. The object scanner is the app I was describing that's used to capture three-dimensional objects. It actually provides a scanning process with a visualization that tells you what you're capturing and really the quality of the capture that you're performing as a 3D capture. And then a calibration assistant, which is to perform eye calibration for optical see-through, meaning that with like the Vuforia, which is an Epson device, or with the ODG by Earsterhout, what it is we provide camera calibration. Eye calibration is really to understand the geometric relationship between your eyes, the pupillary distance, and also the display. And so what it provides is it really improves the accuracy of static registration. When you're looking through eyewear, one of the concerns is that depending on really the angle and the position of the eyewear, when you're rendering onto that, it'll affect the accuracy of the registration of augmented media onto a real-world surface. So calibration enables you to improve that accuracy, and it's customized by the user. Everybody has a unique facial geometry, so it's important to enable them to calibrate. So in talking about eyewear, we support two classes, and it's what I introduced at the beginning. It's optical see-through eyewear and also video see-through eyewear. Now, on the left, you'll see the video see-through examples. We're currently supporting the Gear VR Innovator Edition, so you can use the Note 4 or the Samsung S6 in the Gear VR. We're also supporting Google Cardboard, which is supporting a range of devices. And one of the examples of a cardboard app that we're showing at the booth, if you're interested in seeing this, is the Mattel Viewmaster. So Mattel had come out, if you remember the Viewmaster from like the 60s and 70s, is that it's a stereoscopic viewer that had the experience reels. And remember those? And you would actually click through and you would see a 3D image of whatever, the World's Fair or something. So they brought that up to speed with using augmented reality. And I think you should, if you have the opportunity to take a look at it, because what we're showing with the Viewmaster is what I'm going to be demonstrating today, is the ability to develop an app that blends augmented reality and virtual reality, and it shows how complementary they can be in designing an application. Now, for the optical see-through, these are devices that typically they're running Android, but they're either running it on device or they're running it through a tethered sort of companion appliance or a peripheral. And so this is the ODG R6, and the R7 is coming out soon, and the Epson Vuforia BT200. Now, with both of these, what you'll notice is that the lens itself is transparent, so you're looking onto the real world, and they're using typically like a waveguide that is laid between your eye and the lens, and they're rendering onto that, so that there's a projection of the image onto a lens that's sort of a subsurface below the transparent lens. So the neat thing about these, with the optical see-through devices, they're getting a lot of traction in the range of like enterprise and industrial cases. So it's the matter of someone being in the workforce, having their hands free, being able to look at a console or to look around their work environment and actually see stepwise instructions or warnings or just whatever augmentation of information is relevant to their setting. The Vuforia is actually also seen a lot of interest in the drone community among hobbyists. And what it provides is the ability that you can see the world around you, you have line of sight to the drone, and you can actually then augment the drone's video camera in the device so that you sort of have a secondary, it's almost like a HUD up there. So I'm going to talk about some of the use cases. Now, again, I mentioned the fact that these give you hands-free interactions. Our SDK, in the ability to recognize things in the real world, enables you to bring them into an immersive experience. And so if you had seen Peter Hall's talk yesterday, one of the things that they were talking about is the fact that you have someone in an immersive experience, you're trying to maintain presence, and there's the concern of their bounding environment. You don't want them bumping into things, you don't want them colliding with things. One of the neat things about using AR with this is that you can actually use physical elements of the environment as targets so that you can understand the geometry. You don't have to show it to the user, but it's something that can be used to acknowledge the physical parameters of their immersive experience. And you can also use targets really as controllers in that environment. So here's a video that shows some of this. That's the Viewmaster. That's Cordy Orley. This is an architectural visualization app. And here's some of the interactive modes where I was talking about. We support occlusion detection, so you can actually recognize when someone is touching a target surface or touching something in the environment. That's obviously the Gear VR. This is a good example of an enterprise app. That's the Moverio. That's an example of using stepwise instructions, really. You can understand what someone's looking at. They go through a sequence of instructions to perform a task. Now, one of the forward-looking apps I was talking about, this is an application, it's really a proof of concept that we had developed with BMW, and what it's showing is a digital eyewear application using an optical see-through device. This is based on the ODG, really for providing driver instructions and for basically providing augmentations that enable you to see the world around you in 360, even though you're in the car. We had shown this at the Shanghai Auto Show recently. So that was an interesting one. So that's using Vuforia, it's using the ODG, and we'd actually innovated a type of tracking that's using the interior surfaces of the car to understand the position of the user's head. So it's almost like we had inside-out tracking, and then we had the ability to understand really their orientation, so that as they were looking around, when you saw, for example, the skateboarder next to the door, that we could understand where they were looking and actually accurately register the augmentation into that. So you gave that sort of transparency effect. So really quickly, I know we don't have a lot of time, I'm going to just take you into the Unity environment to kind of orient you as to the nature of the workflow. What I'll do is, basically in setting up a digital eyewear application in Unity using Vuforia, what you'll do is you'll set up a scene for augmented reality, and then you can configure it for digital eyewear. These are all like drag and drop and push button procedures. There's really relatively little coding in this. What you do for digital eyewear is it's a lot like a standard monocular display. You're just configuring it using 2 cameras to provide stereo rendering. And then we have documentation online in our library that if you're using cardboard or gear, provide a few code steps really for integrating that SDK to our own. And what we do is we're going to use really their barrel distortion shader, some of their configuration parameters for stereoscopy, and we can implement logic that enables us to basically hand off the pose between optical tracking and the rotational tracking that like if you're looking at gear, if you're familiar, gear or the cardboard SDK, is that they're using the inertial sensors to provide a rotational tracking pose so they understand the head movement. And what we provide, and you'll see it in the docs, is the ability to sort of gracefully go back and forth between those so that you can transfer from an AR mode into a VR mode and back and forth. And you can also then use AR elements within VR. So let me go into Unity here. Oh, good, it worked. Okay. All right, so let me, what I'm going to do is just quickly take you into this scene. When you're looking at that, you can get this sample online. It's called our mixed reality sample. So if you go to developervuforia.com, you'll see in the digital eyewear section we provide this. This is going to show you really how to implement the AR scene, how to implement VR, and it provides a set of libraries in there that are attached to the objects here that will show you how to, for instance, implement gaze detection, how to implement transitions between AR and VR. So it shows a lot of best practices. And we have another doc that discusses those explicitly. And really, what it talks about is the fact of, if you've seen some of the VR presentations, is how to accomplish, again, a user experience that is going to enable people to sort of gracefully transition between these modes and to comfortably interact with the environment so that they're, you have a good presence with the experience. So when you're looking at this, really the significant elements of the Vuforia extension is that when you import it into the environment, is we're giving you a set of prefabs here. And these, again, encapsulate all the features of the platform. The significant one is really the AR camera, which you can see at the top. The AR camera serves as a proxy between the device camera, the real-world camera, and also our scene camera. It enables you to configure those, and then really it represents it in the scene so that the configuration is applied to the scene characteristics and also affects the device camera. Now, what I've done here, this has all been pre-configured, is brought in the AR camera. The image target here serves to, let me just turn this off really quick. Here's my image target. Here we go. As you can see there, that is the image. I've uploaded that to the target manager. I brought it back into the project. When I drag in the image target, I can configure it to use that image so that when we see this then in the device camera, it'll actually be recognized and it'll be tracked in the field of view of the camera. When you add content to create an AR scene, all you're doing is making that content a child of the target. And so what will happen then is in the local space of the target, when you're tracking the target, it'll follow it within the field of view of the camera. And then we've implemented some logic for really transitioning into a VR world. And so this is the larger scene. What will happen here, and I'll show you, we have a simulation I'm going to run in play mode. You can use a device camera, is to recognize the target, basically use gaze detection, look at an element of the target. It'll understand that you're using ray casting. It understands that you're looking at it, and then it'll transition into a VR mode. So I've added a world scene here, as you can see. And this is really representative of the VR mode. Now, the other element that you'll see here is I brought in the cardboard Unity extension, and I performed a binding step. Now, this is really kind of the significant thing as far as enabling cardboard or gear to work with Vuforia, is if you look here where we have a bind alternate camera, that enables us basically to use another SDK's camera rig. And what we're doing here is I've actually defined a central anchor point using the cardboard head object. And this provides a transform for the user's head. And then you'll see that cardboard also provides two cameras to enable stereo rendering. So what we've done is just made an assignment that cardboard's head serves as the central anchor point for rotation. As you're moving around, when you're rotating the pose of the head, that's really acts as the center. And then we've defined the left and right stereo cameras. So again, what this means is that rather than use our own camera rig, we're using another party's camera rig, and we're going to be manipulating that within the scene. And then I've enabled synchronized pose updates. All that means is that we're getting a pose update from the rotational tracking from cardboard, and we're also getting a pose update from the optical tracking provided by Vuforia. And you just want to make sure that they're basically recognized, or what would you say, that they're affecting the scene in sequence so that they're not colliding, basically. And then the other significant thing is skewing frustum. What this means is that with a video see-through device, you have a single display. It's not actually, you don't have two optical lenses. So what we do is there's a subtle manipulation of the camera frustum so that you are converging both eyes accurately when you see something. So it's important to use that. So what I'm going to show you here, let me just take you into play mode. Vuforia provides a simulation, right? And what it is that you can go into Unity's play mode, you connect a device, a webcam, and then you can use that to do rapid prototyping. And if everything works out, this should show you the scene. So as you can see, you'll notice a little cardboard logo down there. So this is broken into stereo. You'll see that the barrel distortion has been applied right in the center. You see a little point there. That acts as a reticle. That's indicating where your gaze is, right? And I'm looking at everybody here. Now you'll notice as I look at the target, it augments it. That was the content that I added as a child of the image target. And when I look at the center, it highlights that it recognizes my gaze, and it pushes me into the VR experience. Now in play mode, being that we don't have an inertial sensor, there's no tracking coming off of this. But if it was on a device, I have another, actually I can show you here. You can actually prototype using the device itself. So you'll see here. So this is the same app. This is our mixed reality app just running on a device. I can build and run right out of Unity. And then when I look at the target, you see that? Same thing. Highlight it with my gaze. Now the neat thing, one nice thing about cardboard, is now I'm using the inertial sensor of the device. And you can see that what Vuforia's done is that we're no longer using optical tracking, we're actually using the inertial tracking provided by the cardboard SDK. So that's the basic workflow. Essentially, go back to my Mac. It's authoring based. There's very little coding involved. There's a little bit of adaptation to work with the specific, whether it's the Gear OVR SDK or it's the Cardboard SDK, but it's actually very, very simple. I mean, you can literally, if you check out the docs, you can put this scene together in 15 minutes. I'm not kidding. So again, you're going in, you're adding an AR camera, you're adding your targets. You can use the full range of features with mixed reality or our image targets, object recognition, any of it. And then you can use that really to complement a VR experience, whether it's to transition into VR or to provide an awareness of your environment using augmented reality in a VR space. So, do we have any questions? If you could step up to the mic.
Sort of a strange one. Do you find that the targets matter, like what they look like, if it's more simple, if it's more complicated?
It is. So she was asking, really the significance of the target, as I mentioned at the beginning, is that you do need to have a density and distribution of contrast-based features on the card. Like a plain white piece of paper, you're not going to be able to track. A paper with a little dot on it, you're not going to be able to track. But as long as you have some distribution of contrast variation, it's actually pretty robust. This is an example that we use in our samples that is extraordinarily robust. When you go into the target manager, we provide a target rating from 1 to 5. This is a 5. This is one of the stronger targets you can get. But, I mean, any longer, we've refined it to the point that you can work with relatively simple images, like a simple line drawing. What I'd recommend is if you have an image you'd like to work with, upload it to the target manager. You can actually get a view of which features in the show features view, which are being used. And then you can refine it iteratively. If it's not strong enough, just add a little something until you can pick it up. Yeah. Any other questions?
So is the line between the optical recognition and the full VR mode, I guess, at what point can you overlay an entire or 90% of a VR world onto the optical recognition part, onto the...
You couldn't, so what we've run into, as far as sort of running them simultaneously, what we recommend as a practice is to actually make a clean handoff. Not to attempt to, like once you're in the VR world, just use the pose tracking provided by the inertial sensor. You can use our optical tracking to recognize where things are, but we don't actually allow it to influence the head pose, because what we found is there's just, when you're trying to do them sometimes there's too much noise, essentially, that comes up. So they've done a great job in sort of, you know, refining the IMU processing coming out of Cardboard. The Gear is very strong with that as well, so we let them do it effectively. And then when you're back in the real world, we use the optical tracking. Yeah. Any other questions? Okay, thank you.